Binary addition is one of the few topics in this syllabus where the entire method fits into 4 rules, and once you have those 4 rules, you can add any 2 binary numbers of any length. Here they are. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 1 is 0, carry 1, and 1 plus 1 plus 1 is 1, carry 1. That last rule only comes up when a carry has arrived from the column to the right, so you will not need it on the first column, but you will need it constantly after that. Now, the third rule is the one that unsettles people, because in denary, 1 plus 1 is obviously 2. But remember what we established about bases. In binary, there is no digit 2. The symbol simply does not exist. So when a column totals 2, we do exactly what denary does when a column totals 10. We write 0 and carry 1 into the next column. It is the same mechanic you have used since primary school, just happening much sooner because the base is smaller. Let me labor that comparison for a second, because if it clicks, the rest of the topic is easy. In denary, when you add 7 and 5, you get 12. 12 needs 2 columns, so you write the 2 and carry the 1. The carry happens because the column overflowed past the largest available digit, which is 9. Binary works identically, except the largest available digit is 1. So a column overflows the moment it reaches 2. That is why carries appear so frequently in binary addition. You are working in a base where the digits run out almost immediately. If you find yourself writing a 2 or a 3 anywhere in a binary answer, stop, because you have made an error. Every single cell in the answer must be a 0 or a 1. Let us add 2 bytes properly. 0010101 plus 00011010. Always start at the rightmost column and work left exactly as you would in denary. Rightmost column, 1 plus 0 is 1, write 1, nothing to carry. Next column left, 0 plus 1 is 1, write 1. Next, 1 plus 0 is 1, write 1. Next, 1 plus 1 is 2, so write 0 and carry 1. Next column, and now that carry arrives, 0 plus 1 is 1, plus the carried 1 makes 2, so write 0 and carry 1 again. Next, 1 plus 0 is 1, plus the carry makes 2. Write 0, carry 1. Next, 0 plus 0 is 0, plus the carry makes 1, so write 1 and there is nothing left to carry. Leftmost column, 0 plus 0 is 0. Reading the answer off, we have 010000111. Let us check it in denary. The first number was 45, the second was 26, and 45 plus 26 is 71. Our binary answer is 64 plus 4 plus 2 plus 1, which is 71. It matches. Now to overflow, which is the part of this topic that carries the most marks and is answered badly most often. An 8-bit register holds exactly 8 bits, not 9, not as many as it needs, 8. We know from the last video that 8 bits can represent 256 different values, from 0 up to 255. So what happens if a calculation produces an answer larger than 255? The answer needs a 9th bit, and there is no 9th bit. The carry coming out of the leftmost column has nowhere to go. That is overflow. Notice the definition carefully. Overflow is not the computer breaking, and it is not the program crashing. It is the specific situation where the result of a calculation is too large to be represented in the number of bits available. Let us watch it happen. 101100011 plus 010011101. In denary, those are 179 and 77. Rightmost column, 1 plus 1 is 2. Write 0, carry 1. Next, 1 plus 0 is 1, plus the carry makes 2. Write 0, carry 1. Next, 0 plus 1 is 1, plus the carry, 2 again. Write 0 and carry. Next, 0 plus 1 plus the carry. Write 0, carry 1. Next, 1 plus 0 plus the carry. 0 again, carry 1. Next, 1 plus 0 plus the carry. Write 0, carry 1. Next, 0 plus 1 plus the carry. Write 0, carry 1. And now the leftmost column, 1 plus 0 is 1, plus the carried 1 makes 2, so we write 0 and carry 1. But there is no 9th column to carry into. Every bit in our answer is 0, and the true answer, 256, has been lost completely. 179 plus 77 has produced 0. So, what are the consequences? The stored result is simply wrong, and that is the key point. The machine does not stop, it does not report an error by itself, it carries on using a value that is incorrect. In an 8-bit system, 256 wraps around and is stored as 0. In a real system, that could mean a counter resetting when it should have kept climbing, a total in a shop system showing a nonsensical figure, or a sensor reading being interpreted as far lower than it really is. The processor typically sets an overflow flag in a status register to signal that this has occurred, and it is then up to the program to check that flag and respond. If the program never checks, the wrong value flows onward silently. That is why overflow is dangerous, the failure is quiet. The last part of this lesson is logical binary shifts, which are closely related because they can also lose data. A logical shift moves every bit left or right by a given number of places and fills the vacated positions with zeros. Shifting left by 1 place multiplies the value by 2. Shifting left by 2 places multiplies by 4, and by 3 places multiplies by 8. Each place doubles it again. Shifting right by 1 place divides by 2 places divides by 4, and so on. That relationship is exactly why shifts are useful. They are a very fast way for a processor to multiply or divide by powers of 2, much faster than a general multiplication. But here is the part that is examined. Bits shifted off the end are lost, and they do not come back. Take 00001011, which is 11, and shift it right 1 place. The rightmost one falls off the end and is gone. What remains is 00000101, which is 5. 11 divided by 2 is 5.5, and the 0.5 has been discarded because there is nowhere to keep it. Now shift that result back left by 1 place, and you get 10, not 11. The information was destroyed by the first shift. So shifting right then left does not return you to where you started. And if a question asks you to explain why, the answer is that the bits shifted out are lost permanently. The same is true shifting left. If a 1 falls off the left-hand end, the value is corrupted, which is overflow arriving by a different route. Whenever you perform a shift in an exam, write out every bit position carefully and check whether anything fell off either end.